Hello, welcome to this video. This is AP Precalculus, Unit 1A.5. We're talking about complex zeros of polynomial functions. This is part 2 of the lesson. So if you caught part 1, we talked about how to factor polynomial functions and find complex zeros. Today we're going to go ahead and look at some zeros from factored form, as well as getting a rough idea of what a general sketch of a polynomial will look like given the zeros and their end behavior. So without further ado, I just want to go ahead and remind you that we are learning how to construct a graph of a polynomial function, finding the complex zeros, and sketching that graph. So I'm going to go ahead and scroll down to where we left off, which is right here. Before we go ahead and talk about zeros of a polynomial function from factor form, I do want to talk about this idea of multiplicity. Multiplicity of a real zero is how many times the zero's factor appears in the given polynomial function. If we have an odd multiplicity, meaning the zero appears 1, 3, 5, 7, so on and so forth times, then the graph, the function will go ahead and cross through the x-axis. If it's an even multiplicity, meaning it appears 2 times, 4 times, so on and so forth, the graph will be tangent to the x-axis. As the function approaches the x-axis, it will go ahead and bounce off the graph at that zero. So just a couple of examples here. Example number 1, here I have f of x equals x plus 5 to the power of 3 times x minus 2. Here, the x plus 5 factor gives us a 0 of negative 5, and its multiplicity is 3 times. That's how I'm just going to indicate multiplicity. So multiplicity times 3. So I want you to go ahead and see the 0 here at negative 5. And then we also have a 0 here at 2. And this multiplicity is 1 time, and that appears right here. So just notice that our graph does pass through the x-axis at these 0 values. Now it's important to note that there is a distinction between multiplicity of 1 and multiplicity of 3, and you can kind of go ahead and see how the behavior of the graph is here. When you have multiplicity times 3, here we have an inflection point actually at this 0. You can see concave up to concave down, and it kind of looks like a reverse or a negative cubic function. And then here at 2 we just pass through, and this kind of the portion of the graph just looks like a linear function. It only appears once. Kind of a neat connection that a student pointed out. And then we'll go ahead and look at example number 2. Here we have g of x. I have a factor of x equals 1 with a multiplicity times 2, and that 0 is here. And we have, again, a 0 of x equals 6, and that is just multiplicity times 1. So please note the difference between the even multiplicity, right? As I approach the 0, I'm going to touch it and then head back in the same direction, and multiplicity times 1, we just pass through. Okay, so let's go ahead and look at some examples where we are going to find the real zeros of the function, state the multiplicity, and then just state will it cross or will it be tangent to the x-axis at the 0. Yesterday, or in the last video, we went ahead and looked at standard form, a function in standard form, and factoring that in order to find the zeros. Sometimes we get factored form. I don't have to break anything down. It's already in this form. And this is really, really nice. I can go ahead and I can just take the factor here. I have x equals 0. I don't have to solve anything. It has a power of 2. That means it appears 2 times, so multiplicity times 2. And this 0 will be tangent to the x-axis, Okay? I have x plus 4. Okay, I can go ahead and set that equal to 0 and then solve, and we get the 0 of x equals negative 4, and here our function will cross the x-axis. Okay, that's multiplicity times 1. I guess they want us to name the multiplicity, so 1 time. And then x minus 7, this just gives us negative 7. This is positive 7. X equals 7. Multiplicity times 3. And this is odd, so it will cross. Even is tangent, odd will cross. Not too bad. Let's keep going. Example number 2. We have 2x times 8 minus x squared times 3 minus 3x minus 4 squared. If we go ahead to include the 2 or not to include the 2, that is the question. You can, the 2 will never be equal to 0, so you could put the 2 by itself, 2 equals 0. That's a false statement, not true. Or you could just include it here, 2x equals 0. This gives us x equals 0, so multiplicity times 1, and it will cross through the x-axis. The next factor, 8 minus x, we set that equal to 0. It appears 2 times, so I'm going to go ahead and I'm going to add x over to the other side to give us x is equal to 8, which if I use the reflexive property, x is equal to 8, and this is multiplicity of 2. It will be tangent to the x-axis. Okay, and then lastly here we have 3x minus 4. Set that equal to 0. We'll move this 4 to the other side via addition, and then we'll divide. We get x is equal to 4/3. This is multiplicity times 2, and it will be tangent. That's how you find zeros from a factored form of a polynomial. Very, very simple and straightforward. Take each factor, set it equal to 0, and solve. How many ever times that factor appears? So the power will indicate its multiplicity. If it's power 2, that's multiplicity times 2. If it's an even multiplicity, 2, 4, 6, 8, then it's going to be tangent. You're going to have an extrema at that location. Okay, and we'll look at that in a second. And then if it's odd, you're just going to pass through it. Okay, so hopefully that made sense. I want you to go ahead and try these 2 examples. I'll talk through these here in a second. All right, hopefully you pause the video. Here is the solution. So x minus 9, that gives us x is equal to 9, multiplicity times 2, and this is tangent. For x squared minus 9, if we set that equal to 0 and then move the 9 over, we get x is equal to plus or minus 3 by taking a square root of each side. All of these multiplicities are 1. There's 2 zeros there. It's a positive 3 and a negative 3, so 2 separate ones. Both of their multiplicity is 1. Okay, so I mean you could list them out like this. Okay, and then both of these will cross through the x-axis. Okay, so 3 zeros there: 9, positive 3, and negative 3, and that's their behavior. For the multiple choice question, please pause and try this one if you have not already. But we're going to go ahead and look at this. They say the graph of a polynomial function f is shown in the figure, which could be its equation. Well, what you should notice is that we go ahead and we touch the 0 of 0, and it's an extrema. It's tangent there, right? Tangent meaning only touching at that one point. So this should have multiplicity at x squared. So if we look at our options, notice B and C have x squared. Okay, so those are looking good. And then I have a 0 here at 3, x equals 3. So that factor is going to be x minus 3, x minus 3. So our answer, C. Okay. Now, we've reached the second part of our success criteria in the lesson today. If you can identify the zeros, you're good. And then also, hopefully, roping in our last lesson, the end behavior of a polynomial function. We should be able to sketch, give a rough sketch. We won't be able to say where the extrema are, but we should have the end behavior and the zeros pretty nailed down. So here's what we're going to do. We're going to state the values of the zeros, the end behavior, and then we'll sketch the graph. So example 1, x minus 4 to the power of 2 times 1 minus x. Okay, I'm going to go ahead and I'm going to take my factor and I'm going to solve. So x is equal to 4. And this is multiplicity times 2. So at 4, I put a little star there just to indicate multiplicity. That's going to be an extrema, a max or a min. And then I have 1 minus x. If I set this equal to 0, we get 1 is equal to x. So x is equal to 1. Okay, so there's my zeros. There's my zeros. And then we want to go ahead and state the end behavior. End behavior. So in order to do end behavior, you need to know what your leading term is, and I'll abbreviate that LT. So based upon this, my leading term is going to be x times a negative x. That's going to be a negative x to the power of 3. this is negative. It's negative. And what that means is it means that my right side's going to go down, and the degree is power of 3, which is odd. The left side will do the opposite of what the right side's doing. So this is going to go up. Okay, so there's my end behavior. And if we want this in a limit statement, the limit of g of x as x approaches the right side, x going to positive infinity, is going to be equal to negative infinity. This side should be going down. Okay, and then the limit of g of x as x decreases unbounded, meaning x is approaching negative infinity, that value is going to be positive infinity. So this value is going to be coming up here. So I have my end behaviors in place. I want to talk about how do I finish this sketch? Well, remember, if my 0 is multiplicity, that's odd, I'm going to pass through. So I'm going to go ahead and I'm going to pass through 1, and then I'm going to turn around. Doesn't matter where you turn around, we're just making a rough sketch. And then I'm going to be tangent at even multiplicity, which x equals 4 is. So there's a rough sketch of what our graph should look like, okay? All right, here is a practice problem. Please go ahead, pause the video, try this example. All right, here's what your zeros should look like. 2, -3, and -5. We're going to have multiplicity at -5. For some reason, this looks like a 5. My students always mess this up. Make sure you're at 5 here. Then we're at -2, no, -3. -3 and a +2. And then our leading term, the leading term 1, 2, 3, 4, should be x to the power of 4, meaning right side's going up, and since it's even, left side's going to match. So our graph should look something like this. I'm going to bounce off this multiplicity of 2 and pass through, and then pass through. So there's what your sketch looks like. And then if you were curious about the limit statement, this is the left end behavior. It would look like this. And the right end behavior looks like that. Okay? All right, hopefully you did good. All right, last example that I have for you is going back to standard form. So remember, when you have a standard form polynomial function, we need to factor, or I need to break this down. So I'm going to take out a GCF of 2x squared, leaving behind x minus 3. So our zeros from this, I'm just going to take the x squared, is x equals 0. And because it's squared, I have 2 of them. Okay, so multiplicity there. And then x minus 3 gives me x is equal to 3. Multiplicity times 1 right here. Okay, my leading term, this is what's nice about standard form, is that my leading term is indicated. It's indicated, 2x cubed. Okay, so the leading term, 2x cubed, well, that means that the right side, since it's positive, is going to go up, and my left side is going to do the opposite, since it's a power of 3, since it's odd opposite. So left side's going to go down. So our graph is going to look like this. Something like this. Okay, and then the limit statements, the limit of f of x as x approaches positive infinity is equal to positive infinity. And the limit of f of x as x approaches negative infinity is equal to negative infinity. Okay, so that's the main idea. When you have a standard form polynomial function, you got a factor, and then it's business as usual. Okay, please pause me. Please try this example. If you get stuck, check. I'll show you how to factor this, but I want you to try this. Try to factor this here in a second. Okay. Hopefully you paused and tried this. The problem that's throwing this off is the negative. So if you just want to get rid of it, get rid of it. I'm going to take away a negative from everything. I get x to the 4th minus 17x squared plus 16. That kind of makes factorization much easier. Pause and finish this off if you haven't, and I'll continue going. Okay, so with that negative out of the way, now I have x squared minus 16, x squared minus 1. And if I set each of these equal to 0, we get x squared equals 16 and x squared equals 1, which means we have zeros at plus and minus 4 and plus and minus 1 via taking the square roots. Okay, so we can plot these for negative 1, 1, 4. And my end behavior, since it's negative, a negative even, both sides are going down. So it's going to look like this. No multiplicity that's even in this example, so I don't have any extrema at my zeros. They all pass through. Okay, and then again, just to double check your limit notation, the left side is going down, and the right side is also going down. Okay. All right, couple of multiple choice questions. I want you to go ahead, try these, put a guess down, and then I'll talk about the solution here in a second. Okay, for these examples, notice I have a factor here, x plus 5 squared. That means x is equal to negative 5, multiplicity times 2. And then the other factor, the x squared plus 9, if you set this equal to 0, you get x equals plus or minus 3i. So that's imaginary. And just some vocabulary words here that we need to talk about is the word distinct. Distinct means unique. So this function only has one distinct real zero, and that's negative 5. And then it has two non-real. So the answer here is C. One distinct, it repeats twice, but only one. And then we have two imaginary. That's an I. It looks a little funny here. Okay? All right. Last one here. Pause and try this if you have not. Okay, so with this example, I get x equals 0. That's a 0. And then we get x equals plus or minus the square root of 2i. And then lastly, x equals plus or minus 1. If I move this over and then take a square root. So it looks like I have 3 distinct zeros and then 2 non-reals. So the answer, B. The answer is B. All right. Okay. Hopefully you went ahead and learned how to find zeros in this video of polynomial functions and how that kind of relates to their graph. Give me a thumbs up, like the video, subscribe. Catch you in the next video. Peace.